Hey all you calculus fans, welcome to our online Math 400 classroom. Thank you again for being flexible. I know this is not the calculus class you had signed up for in the beginning. This isn't the one I thought I would be doing either. So thank you for being willing to just kind of to go with the flow, and we'll see how everything goes. So my goal for these videos is to not like do an hour long lecture or a 2 hour long lecture, because that just would not be a whole lot of fun to watch. I probably wouldn't even watch them. So I want to try to keep them to at most like 25 minutes. I'll try to do my best to keep the time down from there. But if I have to split a video up into 2 sections, then I will. So we'll just kind of playing it by ear. I've never really done this before. So I've also, I'm tagging videos like from other sources just to give you guys more resources and more things to watch than just me. So hopefully you'll have enough resources out there to still be successful. And you know, if you have any questions whatsoever, please contact me. Email me at any time, Zoom during office hours, and I'll help you as much as I can. You are not alone in this whole entire process. All right, so let's go ahead and get started. So we're gonna pick up right where we left off. So my Monday, Wednesday section, we hadn't yet to cover 4.3. In the Tuesday, Thursday section, we just had the little bit, just the stuff at the end. So you'll have to just skip ahead to that for Tuesday, Thursday. But the rest of you, let's start at the beginning. So 4.3, we're looking at the first derivative test and like how to use it and what does it tell us about the function. So let's look at this function right here. So where is this function actually increasing or going up? So when we give this, you're talking about intervals going from left to right. So from here, so from left to right, you're going up, or it's increasing from negative infinity, and then once it reaches -2, it switches directions and it goes down. And it keeps going down until you get to +2, and then it increases it again. Well, if we looked at the derivative in those intervals, we're going to notice something. Because again, what is a derivative? I keep asking that question over and over in class. It's the slope of the tangent line. So if you drew some tangent lines on either interval, the slope of those tangent lines is going to be positive. So what is the sign of the derivative? Positive. All right, so we kind of talked about this one already, where f decreases. So that's where it's going down. So it's going down from -2 to 2. And if we drew a tangent line in there, it would have a negative slope. So visually, we can connect the two concepts together and actually define it and get a good definition. So for increasing and decreasing, for the definition, if f prime, if it's positive, then f is increasing. And if the derivative is negative, then f is going to be decreasing. And that will always be connected together. Those two things are going to be connected together. So if you know the sign of the derivative, then you know what the graph of the function is going to do. Well, what about where the function switched when it went from increasing to decreasing? Probably shouldn't have erased my graph, but I did. So that would have been at this point and this point. Now, if you drew the tangent line in there, it would actually be like this and this. So those slopes would be 0 because that's where you have a horizontal tangent line. So the derivative itself is now switching around. It's going from negative to positive, but whenever it's switched, that's when the derivative was 0. Well, we talked about that previously in a previous section. What were those things called again when the derivative was equal to 0? Critical numbers. So critical numbers are going to be critical, and trying to figure out the increasing and decreasing and all sorts of stuff. So let's look at an example from example 1. And I don't want to do every single example in the video because I know that's why it would take like an hour or 2 to get through. So I just want to kind of hit some highlights and then the rest of them I'm going to post online. So you'll have 2 sets of notes, the blank copy and then you'll have a completed copy. So you can see everything. So let's look at part B. So g of x is equal to x to the 2/3 minus 4. Okay, so we're going to find the critical numbers of each function, if any, and then find the open intervals where the function is increasing and decreasing. So the critical numbers, we have to take the derivative and set it equal to 0 and then solve for x. So the derivative would be 2/3 x to the negative 1/3, and then the negative 4 would just go to 0. So there's your whole derivative, set it to 0, and then we'll solve for x. And then just as a reminder, anytime you have a negative exponent, flip it to the denominator, and then you're solving for what makes the derivative either 0 or what makes it undefined. So in this case, it's what makes it undefined, and that's the critical number we're after. So that's going to be right at your x equals 0. So that critical number is where the derivative is 0. We're interested in where the derivative is positive and where it's negative. So we're going to do something similar to what we did in Math 370 if you had me for that. And we're going to do a number line test. So you're going to put your critical numbers on the number line, and then you're going to test the intervals you just created to see if they're positive or negative. So we just split the number line into 2 halves. You have the negative side and the positive for numbers. So choose any number you want as long as it's less than 0. So negative 1. And then on this side, you can choose any number you want as long as it's bigger than 0. So positive 1. Your test numbers, these blue numbers, you're going to plug them all the way back into the derivative, and all you care about is if it comes out positive or negative. Just the sign of the answer. So if I plug in the negative 1, it comes out as a negative. If I plug in the positive 1, it comes out as a positive. So now that you know the signs of the derivative, you know what the function is going to do. So it's increasing wherever you have a positive interval, so from 0 to infinity. And it's decreasing when you have a negative interval or negative infinity up to 0. And that's pretty much how they're all going to go. You just got to find the derivative, get your critical numbers, and test them. All right, so let's go over what the first derivative test actually does, because a lot of people think it's this, because we just use the first derivative, but it's not quite that. So the first derivative test, if you look at what your notes say, right at the top inside the box, it says the test determines the relative extrema. That's all the first derivative test does. It just gives you the relative extrema. It doesn't say anything about increasing or decreasing. So what we just did, that last example, was not the first derivative test. If we found the maximums and minimums, then we are using the first derivative test. So this is what it says. So suppose that C is a critical point of a continuous function and f is differentiable at every point in some interval containing C except possibly at C itself. So C, even though it's a critical number, or critical point, might mean that's where the derivative is, it's 0, or it could also be undefined. So the first one, if f prime switches from positive to negative at C, then f has a relative max. Which should hopefully kind of make sense. Because if the derivative is switching from positive to negative, that means your function is switching from increasing to decreasing, so there's some sort of maximum right at the top of the hill. So number 2, we just got to flip-flop some of the words. So if the derivative switches from negative to positive at C, then the function has a relative min. Because now you have the reverse situation. It's going from where the derivative is negative, or where the function decreases, to where the derivative is positive, or the function goes up. And now you've got the bottom of the valley, or a minimum. Well, there's a third case. So can you guess what it is? So if the derivative does not change in sign, so it stays positive or stays negative, then f does not have a relative extrema. So if it doesn't change its sign, it's not a relative max and it's not a relative min. And we saw one of those before. Remember this fun graph of x to the third? Well, we said earlier that x was a critical point, so that's where the derivative is 0, but the function didn't give you a relative max or relative min because it didn't switch from increasing to decreasing or the other way around. All right, so let's go ahead and look at an example and use the first derivative test. So find any relative extrema, find any relative max and min. So we need the critical numbers just like before. So 2x minus 6. So set your derivative equal to 0 and solve for x. Now, if you just want the relative max and mins, we're still going to set up a sign chart. because we want to know where the derivative is switching and how it switches. So just like before, stick your critical numbers on there, and then choose any number you can that's less than 3. So let's go with 0. And then choose any number bigger than 3. So let's go with 4. Now these test numbers, you're going to plug them straight back into the derivative, not your original function, but the derivative, and just see how it comes out. So if you plug in a 0 for x, it comes out as a negative. If you plug the 4 in for x, it comes out as a positive. So right here, you have a sign change. It went from a negative to a positive. So according to the first derivative test, you have a relative min at the point x is equal to 3. And it wants the whole point. When it wants maxes and mins, you've got to give them the whole coordinate. So it occurs when x is 3, and now you got to get the y value. So anytime you know the x, you plug it back into the original function. I think it was that. Yep. So now you plug the number into the function to give you the y value. So it'd be 9 minus 18, or negative 9. All right, I wish I could ask you if there were any questions, but I can't. So let's just move on to another example. So example 3, now we're going to kind of combine everything into one problem. So find where the function increases and decreases, and then locate any relative extrema. Let's get some more room. So our function, we'll go with example B, e to the x plus e to the negative x. So we need our derivative. So the derivative of our function is going to be e to the x minus e to the negative x. So now we set it to 0, and then we can solve for x. So we're going to move this e over to the other side. And then using your math skills, what cancels out an e? Well, an ln. So we'll take the ln of both sides. So x equals negative x. And sometimes with calculus students, they see this equation and they freeze because they don't know what to do with it. So don't forget your algebra. We're going to add x over to the left. So you get 2x is equal to 0. So x is 0. All right, so we're going to make that number line, and we're going to get everything we want from this sign chart. So plug in some test numbers. So -1 and 1. And again, where do we put these? Back into the derivative. So if you plug in -1 into the derivative, it's going to come out as a negative. If you plug the +1 into the derivative, that comes out as a plus. It's not always a minus first. I know the last 2 examples that's how it happened, but not every time. So from this sign chart, we can get the intervals of increasing and decreasing. So it's increasing from 0 to infinity. It's decreasing from -infinity up to 0. And if you look at your signs, the minus and the plus, that's a sign change. It's switched from negative to positive, so that is a relative min. So it's happening when x is equal to 0. So go back to your original function, plug in 0, and the y value comes out as a 2. Now, it's also important to note that these things, these are intervals. And when you start talking about the extrema themselves, those are actual